Hi, Assalamualaikum. So today, me and my friends are going to explain on volumetric analysis, specifically titration of chlorine from swimming pools in this video. So these are my group members, Marshall, Nancy, Rachel, and me myself, Sophia. So in this video, we will be going through the introduction, the theory of volumetric analysis, the methodology of titration of chlorine, and keynotes when it comes to it, as well as the conclusion. Titration is a quantitative analytical technique used to determine the concentration of a substance in a solution by reacting it with a standardized reagent. In water treatment, especially in swimming pools and drinking water systems, titration is a reliable method for measuring chlorine levels to ensure water safety. Chlorine is commonly used as a disinfectant because it effectively kills harmful bacteria and algae. However, maintaining the right chlorine concentration, which is typically 1 to 3 ppm for pools, is crucial as too little chlorine fails to sanitize, while too much can cause skin and eye irritation. Titration provides an accurate and cost-effective way to monitor chlorine levels compared to test strips or digital meters. The most common titration method for chlorine testing is iodometric titration, where chlorine reacts with potassium iodide to release iodine, which is then titrated with sodium thiosulfate. A starch indicator helps identify the endpoint when the blue-black color disappears, allowing precise calculations of chlorine concentration. This method is widely used in pool maintenance labs, water treatment plants, and environmental testing due to its high accuracy, reproducibility, and affordability. In this presentation, we will demonstrate how titration can be applied to measure free and total chlorine levels in swimming pool. So what is actually volumetric analysis? Volumetric analysis, also known as titrometry, is a fundamental quantitative chemical technique used to determine the concentration of an unknown substance in a solution. This method involves the precise measurement of volumes of reacting solution to reach a stoichiometric equivalence point, where the amount of titrant added is chemically equivalent to the analyte. The technique relies on standardized solution, which is the titrants, of known concentration, which react with the analyte in a well-defined chemical reaction. Volumetric analysis is valued for its accuracy, simplicity, and cost-effectiveness, making it a cornerstone of analytical chemistry. In this video, we focus on its application in chlorine determination in water samples, demonstrating its practical significance in maintaining public health and safety. So these are the types of titration that falls under volumetric analysis. The first one being acid-base titration, the second one being redox titration, which is the one that we will be explaining more on, as titration of chlorine falls under redox titration. The third one, complexometric titration, and lastly, precipitation titration. So redox titration, which is short for reduction oxidation titration, is a type of volumetric analysis where the reaction involves the transfer of electrons between the analyte, which is the substance being analyzed, and the titrant, which is the standard solution. The equivalence point is reached when the moles of oxidizing agent equals to the moles of reducing agent. So the key concepts of redox titration are oxidation and reduction, oxidation being loss of electron and reduction being gain of electron. Titrant and analyte roles, which is the titrant is a standard solution of a strong oxidant, and the analyte is the unknown concentration of a reductant or oxidant. The equivalence point detection, which is the indicator, some redox titration use specific indicators, such as starch for iodine, and for self-indicating, some titrants, such as potassium manganese, are colored and act as their own indicator. The steps for redox titration consist of number 1, prepare the titrant, number 2, mix the analyte with an acid or base, third, to titrate slowly while monitoring color changes, fourth, record volume of endpoint, and lastly, calculate concentration using stoichiometry. And the advantages and limitation. For the advantage, highly accurate for electron transfer reaction, wide range of detectable analyte, such as metal, organics, and gases. and for limitations, requires careful pH control, such as potassium manganese needs sulfuric acid. And some systems need inert atmospheres, such as to prevent oxygen interference.
Hello everyone, my name is Nancy. Now we are going to apply the volumetric analysis by using this experiment, which is titration of chlorine. First of all, let me introduce to you what is this experiment. Basically, the titration of chlorine commonly performed using an iodometric titration. It is a precise method to determine the concentration of free of or total chlorine in sample water, such as swimming pools or drinking water. In this redox-based technique, chlorine oxidizes potassium iodide to release iodine, which is titration with a standard disodium thiosulfate solution. The objective of this experiment is to determine the free chlorine and total chlorine concentration in pool water using iodometric titration. The materials require a pool water sample, potassium iodide crystal, sodium thiosulfate solution, starch indicator solution, acetic acid, burette and stand, conical flask, pipette or measuring cylinder, and lastly, white tile. Let us move on to the first procedure, which is testing free chlorine. Step 1. We need to collect the water sample. Remember to use the clean container to collect 100 ml of pure water. Next, we need to add potassium iodide into the sample. Add in about 1 or 2 grams of potassium iodide to the sample. Swirl gently to dissolve. Step 3. Observe the reaction. Free chlorines react with potassium iodide to release iodine, which turning the solution into yellow-brown. Next, step 4. Titrate with sodium thiosulfate. Fill a burette with 0.101 mole of sodium thiosulfate. Slowly add thiosulfate while swirling until yellow-brown color fades to pale yellow. Step 5. Add starch indicator. Add in about 1 to 2 ml of starch solution, which turn deep blue-black due to iodine starch complex. Step 6. Continue titration to endpoint. Continue adding sodium thiosulfate dropwise until the blue-black color disappears completely. Record the final reading of the burette. For the final FAT procedure part 1, Step 7. Calculate free chlorine. Free chlorine equals to volume of sodium thiosulfate used times molarity of sodium thiosulfate times molar mass of chlorine times 1000, which divides by some sample volume.
For part 2 procedure is testing total chlorine. Step 1. Acidify the sample by taking another 100 ml of cool water and add 1 to 2 ml acetic acid to convert combined chlorine into a free chlorine. And step 2. Repeat titration step 2 to 6. Follow the same procedure as the free chlorine. Record the volume of sodium thiosulfate used as volume 2. Step 3. Calculate total chlorine in ppm by using total chlorine in ppm formula, which is volume 2 times molarity times 35.45 times 1000 divided by sample volume. And step 4. Determine combined chlorine. Combined chlorine equals to total chlorine minus free chlorine.
Today we'll be experimenting for residual chlorine. As you can see, we have taken acetic acid, sodium thiosulfate, indicator as potassium iodide. We have taken starch. The burette is filled with standard sodium thiosulfate solution. We have taken 100 ml tap water as a sample in the conical flask. 5 ml of acetic acid is added to the sample. A pinch of potassium iodide is taken and is added to the sample. There's a slight change in the color. It has changed to pale yellow color. Now this will be titrated against standard sodium thiosulfate solution. As you see, from dark yellow color to it has changed to pale yellow color. The color has faded out. So after this, add the starch. 1 ml of starch is measured and is added to the same sample. As you can see, it has turned to dark blue color. Now again, this is being titrated against sodium thiosulfate solution. Titrated until the blue color disappears or fades out. Note down the burette reading for the calculation of amount of residual chlorine that is present in the sample. Repeat the same procedure for the blank solution. Note down the burette readings for the blank solution, where blank solution is your distilled water. Then deduct the blank solution reading from the actual reading solution in order to get the residual chlorine value.
For expected result, prechlorine ideal range for pool water is 1 to 3 ppm and action required safe for use. Combined chlorine less than 0.5 ppm. Action required, shock treatment needed if higher than 0.5 ppm. For keynotes in chlorine titration, the reason why starch is added late, for scientific reason, it is because starch forms an instant blue-black complex with even trace amount of iodine. If it is added too early, the strong color can mask subtle change near the endpoint. The iodine starch complex has low dissociation kinetic, potentially causing a lag effect, where extra titrate is needed to fully clear the color. Best practice is add starch only when the solution is a pale straw color, after 90% iodine has reacted. This gives a sharper, more accurate endpoint. For pro tips, use freshly prepared starch solution, which is boiled then cooled. This shredded starch may give fuzzy endpoint. The reason why acid is added for total chlorine test. The chemistry behind it, prechlorine react directly with potassium iodide. Combined chlorine require acidic condition for labeling iodine and make it this chemical equation. Monochloramine react with potassium iodide and hydrogen ion to produce ammonium ion, iodine, potassium ion, and chlorine ion. For pH control, acetic acid maintain pH 3 to 4, ensuring complete chloramine breakdown without excess acid interfering. For common mistake, omitting acid will underestimate total chlorine by chloramine concentrations.
Key notes in chlorine titration. Sodium thiosulfate standardization. Why standardization is critical? Sodium thiosulfate solutions decompose over time, which affects accuracy. This happens due to, first, microbial action. Bacteria consume the thiosulfate. CO2 absorption. Carbon dioxide dissolves in a solution, lowering the pH, which causes chemical breakdown of thiosulfate. Third, light exposure causes photodegradation, which is breakdown under light. Standardization method. A. Titrate a sodium thiosulfate solution against a primary standard, which is potassium iodide. B. Reaction steps. Potassium iodide reacts in acidic medium with iodide to form iodine. C. The generated iodine, I2, is then titrated with sodium thiosulfate to determine its exact concentration. Frequency. Re-standardize weekly to ensure accurate and reliable titration result. Endpoint troubleshooting. First fading endpoint, which is blue, returns after 30 seconds. Cause: oxygen reoxidized iodide to iodine in acidic solutions. Fix. Complete titration rapidly after acid addition and do not pause near endpoint. Second, no color change. Causes expired Ki, degraded starch or insufficient chlorine. Fix. Test reagents with non-chlorine, for example, dilute bleach. Third one is over titration. Sign. Solution turns pinkish from thiosulfate excess reacting with starch. Fix. Discard sample and restart. Over titration cannot be reserved. Interference and how to mitigate them. First, oxidizing agents, for example, bromine, ozone, etc. Interference. These substances can react with potassium iodide, producing iodine and giving falsely high chlorine readings. Solution. Use the DPD method, which is more selective for free chlorine and avoids this interference. Second, organic matter interference. Organic matter can consume chlorine, reducing the actual chlorine available to react with Ki, which leads to lower measurable levels. Solutions. Filter the sample using a 0.45 UM membrane filter to remove turbidity and organic particles before testing. And the third one is high pH, which is more than at interference. High pH slows down the reaction between chlorine and Ki, which causes incomplete iodine release and underestimation of chlorine levels. Solution. Acidify the sample to about pH 4 before adding Ki, ensuring complete and rapid iodine generation. Advanced tip: differentiating free vs combined chlorine. First, sequential testing step. A. Free chlorine. Titrate immediately after potassium iodide is added without acid. This measures only the chlorine that is immediately reactive. B. Total chlorine. Repeat the titration, but this time with an acidified sample. This acid helps release both free and combined chlorine, giving the total chlorine level. C. Combined chlorine. This is calculated by subtracting total chlorine minus free chlorine is equal to combined chlorine. Combined chlorine includes forms like chloramines, which are less effective disinfectants. Why is it matters? If combined chlorine is high, it indicates chlorine lock. This means the sanitizer is not effective, the chlorine is bound and not free, and the system needs shock treatment to break the bonds and restore sanitation. Safety notes. First, Ki handling. Solid Ki is hygroscopic and it is stored in the desiccator to avoid clumping and inaccurate measurements. Second, acid precautions. Always add acid to water, not water to acid, to prevent violent reactions and splashes. This follows standard lab safety rules to manage exothermic, which is heat releasing reactions. Third one is waste disposal. Acidic iodine waste should be neutralized using sodium bicarbonate, which is baking soda. This ensures safe disposal and avoid environmental or chemical hazard. So for the conclusion, iodometric titration serves as a fundamental volumetric analysis technique for accurately determining chlorine levels in water samples, such as swimming pools and drinking water. This method exemplifies the core principles of quantitative chemical analysis, where a standardized solution reacts stoichiometrically with iodine liberated from the chlorine-Ki reaction. The precise measurement of titrant volume allows for calculating chlorine concentration with high reliability, demonstrating the importance of volumetric analysis in real-world application. That's all from us. Thank you.